The paper number 13, titled
Thank you very much.
Experimental Investigation of Locomotive Efficiency of a Soft Robotic Eel with a Largely Passive Body, from Dinh, Quang, Nguyen, and Van and Ho. So please, you can unmute and share your screen.
Yes. Hello, everyone. Can you hear me?
Yes, loud and clear.
Thank you. So, just a moment, I will start sharing my presentation. Okay. Did you see my screen?
Yes, we can. You can.
Okay. So today I will talk about our research on locomotive efficiency of a short air robot with largely passive body. Okay. First, I will make a brief introduction about soft U robot design. Soft U robot design. The soft U robots construct from a series of soft actuators and use punch control signal with the suitable sitting phase to create the propagation waves from head to tail to make to moving forward or backward. You can see here the app robot design consists of 3 segments, in which head segment contain 2 pair of actuator. The other contain only 1. Why that? Why we design with the head segment have 2 pair of actuator? Because the head segment play a role of weight stroke. So we need to use more longer. When it bend, it will release more energy, and we will make swimming efficiency. In our previous research, the software were fabricated and investigated on anguilliform movement ability. Like this. The result is presented here. The robot shows the best performance at 1.25 Hz with the sitting phase of 50% and air pressure at each segment like this. And the height velocity was 10.5 centimeter per second with the lowest COT of 80.84. A question is whether the robot still work efficiently if the body partly damaged, like we deactivate 1 pair a tail or 2 pair to lower pair, or it can be damaged when it's working. We know that natural air and rigid elongated body robot cannot swim efficiently with the partly damaged body. However, due to flexible and uniform body, soft elongated body might swim efficiently with a partly damaged body. These phenomenon results in 2 merits. The first one is save energy for long journey tasks. We can deactivate lower pass and the robot is still working. Or the second one is enlarge the working condition. This means the robot still works normally with partly damaged body. Therefore, it's worth to investigate the swimming ability of the robot, of the soft air robot. Oh, sorry. Yeah, we can see the change in my presentation.
No, I think the slides actually stuck in the first. So
Sorry,
maybe you have to see. Okay, now we can see on the four.
You can check.
Now it moved.
Okay, sorry. In our previous research, swimming efficiency of the air robots with partly damaged body were investigated. We deactivated the tail of the robot. In that report, only tail segment were deactivated. And this is moving of the robots. You can see it's interestingly, the result indicated that at the same working condition, the robots with passive tail shows a better performance than that with full activation. The soft robot with passive tail has a higher velocity. You can see you can reach higher velocity and lower COT. This means it consumes smaller energy for longer distance movement. So in this research, we plan to evaluate swimming efficiency of the soft air robot at higher passive level. Mean we will deactivate a half body and investigate the swimming efficiency of the robot. Soft actuator. You can see this is the soft robot use. Soft actuator were fabricated by Dragon Skin 30, then affixed asymmetrically along the polyethylene ribbon to form the robot body. In this study, only head segment were activated. We use a camera to record the robot movement for robot velocity calculation. And MATLAB was used to extract the consecutive images to analyzing the robot midline kinematics, air pressure, and electrical energy were recorded to calculate COT. This is the result of swimming velocity and COT. We can see that is the highest velocity at 4 frequency dropped to 65 kilopascal. That's 65. Among them, the highest velocity were at 1 Hz is dropped to 12.46 centimeters per second. This value is higher than that of fully active body. You can see the movement of the robot. This is midline kinematic of the robot body. This is corresponding to the highest velocity at 1 Hz. Midline kinematic of the air robot at this condition does mimic clearly the angular from locomotive. Midline kinematic lies the fully one and the active tail. You can see it's angular form movement. We have creates the sinusoidal wave from head to tail with the increased increment of the amplitude displacement. And this one is not clearly, but it's better than 3 the other. In this one, You can see the lateral movement too big, so the velocity will lower. As the result here, the velocity is quite lower. On in the other, the frequency is too high, so it cannot, it don't have enough time to propagate the wave from head to the passive tail. So it's also the low velocity.
What if it's still in our world? What if we locked him out here with us?
Sorry.
Is everything all right? We see slide number 8.
Sorry.
I'm just asking if everything is all right with the presentation. Because, we're stuck in slide number 8.
Sorry, can you hear me now?
We can hear you and we can see you. Yes. Can you hear us from this side?
Sorry.
Can you hear us from this side? Hello?
Sorry.
Yeah, we can still hear you and we can see still a slideshow. Maybe you can
problem with my computer. Sorry.
All right, maybe you can make some concluding remarks because it's time that you only have some seconds to finish the presentation. So if you would like to conclude it, that would be nice.
Can you hear me now?
Yes, we can hear you.
Okay, then. You also see. Can you also see my screen sharing? Okay, so I will come to the comparison. This is a comparison table of three working modes. You can see the highest velocity drop to the mode 1 when we have a passive tail, and the best one is the COT bad one drop to the mode 2 with a half of a body is passive. So it's both of them is higher than the fully active one. It's very interestingly. So this result indicated that the working mode is valuable for designing an anterior design of this robot, since it consumes the least energy compared to the other mode. Finally, I will make some conclusion. The software robot swimming with one-half passive body were examined. The head segment were considered as the wave stroke, and the rest play as the wave propagation section passively. Differing from the nature and rigid robot ones, the software robots with a large passive body is able to perform good swimming efficiently. And the last one, with one-half passive body, the robot velocity reaches the peak at 12.46 centimeters per second, with COT of 9.39 compared to that of full active one is at 10.5 and 18.83. It's much better. Thank you very much.
Thank you very much as well. I would like to ask if there is any short questions because we only have a minute. And of course, you can write also in the chat if there is something that you would like to ask.
Yeah.
Yeah, as you can see, Manuel Silva asks, what is the meaning of COT?
COT mean cost of transport. Mean we can say that the robots win how many energy the robots use to move in the unit length.
Mm-hmm. All right.
When we have a lower cost of transport COT, mean we have the best locomotion strategy. Use less energy for longer distance.
All right. Thank you very much. I think that concludes this presentation as well. We are just on time, so I would think I will just move to the next one. Thank you very much for everyone.
Thank you. Sorry for my problem with my
Completely okay.
computer.
It happens. It happens with these online systems. It happens all the time. It's completely right.